There is a buoyant force on any object that is submerged in a fluid. And this fluid could be water or air or oil or anything really. And this buoyant force is the force that acts upwards on an object. So this is what makes objects float in water. And it's because the lower you go in the fluid, the higher the pressure is. So there's more pressure pushing up on the bottom than there is pushing down on the top. And the net result is that there's a net force upward. And we've seen that the buoyant force increases as the density of the fluid increases, because the buoyant force is equal to the weight of the object. Or sorry, not the weight of the object, but the weight of the fluid that's displaced. That's what you kind of think it's going to be, is like we tend to intuitively think that the more massive an object, the more buoyant force there will be acting upwards on it. But the buoyant force really doesn't depend on the weight of the object, it only depends on the volume of the object. Because the volume of the object is equal to the volume of fluid that is displaced. And what displaced means is just that the fluid has to go somewhere else. It can't be where the object is. There's a lot of interesting stuff that relates to buoyancy. And we're going to look at a few different situations in this video. Compare a few situations. First of all, let's look at what the buoyant force looks like on an object that is more dense than water compared to an object that is less dense than water. Well, the main difference here is that an object that is more dense than water is going to sink in water, while a less dense object will float. So here's a dense object, and it has sunk all the way to the bottom of the ocean, or whatever. And because it's very dense, it must be pretty heavy, so there's a lot of gravitational force acting downwards on the object. And the buoyant force acting upwards would be less than that. So if this thing was just released from a ship in the ocean and it was just in the middle of the ocean, there would be a net force downward. That net force would be the mg here minus the FB, the buoyant force, and there'd be a net force. And that thing would have to be accelerating downward. But when it's on the bottom, it's obviously not accelerating. And that's because there's the normal force still from the bottom. And we know that if it's not accelerating and it's just sitting on the bottom of the ocean, that there is no net force on it. So in this situation, the buoyant force FB plus the normal force Fn would be equal in magnitude to the gravitational force mg. Okay, now let's look at an object that is less dense than water. So what I'm going to do is, let's just pretend this object suddenly becomes hollow. So it suddenly becomes very, very light and not dense. So its gravitational force is going to decrease a whole lot. Its gravitational force may only be this big. And the buoyant force now is going to be much greater in magnitude than the gravitational force. So now we have a net force acting upwards, which accelerates the object upwards. So if this not dense object was on the bottom of the ocean, somehow it's going to start shooting up to the top. When I was a kid, we used to go on the diving board and hold on to a basketball or a volleyball or something as hard as we could and jump way up in the air and hold on to that ball as we took the ball underwater, and and it's kind of hard to hold on down there because there's a lot of buoyant force on a hollow ball. That ball wants to shoot up to the surface, and you either hang on and you take a quick ride back up to the top of the pool, or it gets ripped out of your hands by the buoyant force, and that ball goes shooting up into the air. So that's what's kind of happening to this object here. It shoots up till it gets to the top of the water, Maybe it shoots up in the air a little bit. But then we know that it's going to end up just floating there. So think about this. If we just saw that the buoyant force on this object was greater than the gravitational force, and we saw that therefore there was a net force upward, there must be an acceleration upward. But if it's just floating here, there's no longer any acceleration upward. So that means there must not be a net force upward. So what happened to the buoyant force? We know it must have decreased because, well, the weight didn't increase any. We still have the weight mg acting downward, and we know that since it's floating and not accelerating up or down, the buoyant force must be exactly equal and opposite, of equal magnitude to the gravitational force. And the reason the buoyant force is less when it's floating than when it's totally underwater is because less fluid is being displaced. When an object is completely underwater, the amount of fluid displaced is the volume of the object itself. But when an object is floating, it's only displacing a volume of fluid like that. So it might be just displacing half as much fluid, and therefore the buoyant force is half as much. And we know the lighter something is, the more it'll stick up out of the water. And this is how boats work. Or if the density of the object is closer to the density of water, 90% of the object will be underwater, kind of like an iceberg, for example. But in any case, whenever an object's floating, that means that the buoyant force is equal to the gravitational force. Alright, our second comparison. Something with a large volume versus something with a small volume. So let's compare two objects that are composed of the same material. So let's just say we have a large cheddar cheese block in the swimming pool, and we have a small cheddar cheese block in the swimming pool. And this one, the big one, is going to have a larger buoyant force because it's going to displace more water. And that buoyant force is equal to the weight of the water displaced. So the weight of the water that has the volume of this big cheddar cheese block. But the buoyant force on this one is equal to the weight of the water displaced by the smaller volume of this smaller cheddar cheese block. So that's pretty simple. Alright, our third comparison, a floating object versus a sunken object. I kind of already talked about this with the basketball. But let's just think about a beach ball for a minute. Here's the water, here's the beach ball, you throw it and it floats because there's only a very small amount of buoyant force because it's only displacing a very small amount of water. So the buoyant force is equal to the gravitational force of that water, which isn't a lot of water. It doesn't take a lot of buoyant force to float a beach ball because the buoyant force it takes is equal to the weight of the beach ball, and it's not very heavy. So there's a small buoyant force equal in magnitude to a small gravitational force. But you might say to yourself, I've tried to push a beach ball underwater and it's really hard, so there must be a lot of buoyant force that a beach ball has. And that's kind of true, but it's because you're actually pushing it down. The more you push it down, the more water is displaced, the more fluid is displaced, and therefore the higher the buoyant force. So the buoyant force actually increases the more you push it down, and the more water gets displaced here. So if you were to fully push that beach ball underwater, the buoyant force would be equal to the mass times gravitational force of the water. Sorry, let me repeat that. The mass of the water times the acceleration of gravity. Because that mg of the water is the gravitational force on the water, which is the weight of the water, which is the buoyant force on the beach ball. And finally, our last comparison, an object, what is its buoyant force in air compared to its buoyant force in a liquid like water? Well, what if that beach ball were to be entirely out of the water? We're batting that beach ball around at a baseball game, say. So it's getting batted around through the crowd. There is still actually a buoyant force on the beach ball because it is displacing a fluid. That fluid just happens to be the air. And in this case, the buoyant force on the ball is pretty darn small because that air doesn't weigh a whole lot, but that buoyant force is equal to the weight of the air displaced. So in this case, it would be the m of the air times g. This mg being the weight of the air. The reason it's not obvious to us that there's a buoyant force on objects in the air is that almost all of the time the gravitational force on the object is greater than the buoyant force, so they fall to the earth. This is the weight of the object. That is a vector much larger than the buoyant force. Although there are situations that we know of where the buoyant force of an object in air is actually greater than its gravitational force. For instance, a hot air balloon or a blimp. The reason you put helium in a blimp is that helium is less dense than air, so the gravitational force on this blimp is very low because there's all this very light gas in there. And so that's of the helium. And the buoyant force is, in this situation, is equal to the mass of the air displaced times gravitational acceleration. So this buoyant force on the blimp is greater than the gravitational force on the blimp, and that causes an acceleration upwards. But I guess it wouldn't want to constantly be accelerating up, or it would just go away. It would go bye-bye. So to keep the blimp at a constant altitude, the buoyant force would have to be equal to the gravitational force, so it doesn't accelerate up or down. I think that floating on air is a thing that people say, but in the sense of being above the air, that's kind of hard to do because something that's in the air, like a blimp that's floating, is always going to displace a volume of air equal to the volume of the blimp. It's hard. I mean, you don't have a situation where the blimp is displacing some air on the bottom like it would in water. It's always going to displace the whole volume of the blimp in air. Okay, what I'm trying to say is that the volume of air displaced by a blimp or a weather balloon is always going to be equal to the volume of that blimp or weather balloon. But what changes is that when the weather balloon gets really high, the density of the air decreases. So even though it displaces the same volume of air, the buoyant force would decrease if it didn't expand to displace even more air. Be sure you check out the link to the NASA space balloons somewhere in this PowerPoint presentation, because that thing is really fascinating. It starts off with only a small fraction being filled with helium. So most of it is just like a shriveled long part that doesn't have any air in it. I mean, air or helium. And then it's just like this top part that has some helium. And at ground level, that's enough to get the balloon lifted off the ground. Because at ground level, the air that is being displaced here is dense and is heavy. So that weight of the air that gets displaced here is equal to the buoyant force, and that buoyant force is enough to lift the balloon. And as the balloon gets farther and farther up, the atmosphere gets less and less dense, and the balloon expands more and more until it just becomes gigantic, like multiple football field size. But the buoyant force, when it's very high altitude and very gigantic, is still about the same magnitude as the buoyant force when it was all shrivelly on the ground, because it has to displace more air to have that same buoyant force because the air is so much less dense.